Welcome to Chapter 4, Applications of Differentiation. We've learned all of our derivative rules and now we're going to be applying them. In Section 4.1, we're going to talk about extrema, and in this particular video, extrema and the extreme value theorem. So what are extrema? It's a cool mathematical word and it means the extremes. The extremes are any of the lowest points or highest points. So in math, lowest points are minimum or plural minima, and the highest points, those are called a maximum, and plural, we say maxima. We have a couple different types. An extreme may be a relative or an absolute, and we can also check out the endpoints. So let's talk about the extrema. Here's a little bit of what we just talked about. Extrema are the extremes on a function. We call them maxima and minima. This just means multiple maximum points. Same thing, this is just plural for minimum points. They can be either relative or absolute. They can occur, and we'll talk about critical points, they can occur at the critical points of a function and or the endpoints if we do have an interval from one x value to another. And then extrema can be found either visually, just from looking at the graph of a function, or algebraically. Here is a function that is graphed on an interval from one x value here to another. Those x values don't really matter. This is just the general idea of what extrema are. And we can see that instead of only using the terms absolute and relative, there are synonyms for those in mathematics. Absolute may also be referred to as global, where relative might also be referred to as local. From here on out, I will refer to them only as absolute and relative, as that is what most books, including your textbook, refer to them as. So we can see that along the way here of this function, the absolute tallest point, or the absolute maximum, occurs here. Now, can there be more than one absolute maximum? Yes, there actually can be. That's if we have the same y value occurring again. We don't have that. This is the only one. The absolute minimum value is the absolute lowest point on this interval, and it occurs here. The relative extrema, we can have a few of those, and this is an interesting idea. A relative maximum, here's one, it occurs when at the highest point in just a small area. So we can see that this is a little hill here, and this is the top point of that hill. While this is not the highest point on the whole function, this one is over here, it's still the highest point in its general area. It's sort of like if this person here was the tallest person in their class, but they might not necessarily be the tallest person in the school. The tallest person in the school is over here. So we also have another relative maximum, same idea, occurring at this endpoint here. Yes, extrema can occur on endpoints. This endpoint here is the tallest point in its general area. Relative minima follow the same idea in that they're the lowest point in just a small area. So right here we have a relative minimum occurring because it's like the bottom of a U here. It's like the bottom part. It is the lowest point in this small area. This endpoint over here on the left is also a relative minimum value because it's the lowest point in its area. Now, how do we talk about extrema? The actual extreme value, either the max or the minimum value, is the y value. It's the height of the function. So let's say that this coordinate point over here, our absolute maximum, let's say that this coordinate point occurs at -5, 27. We would say that the absolute max is 27, and it occurs at x equals 5. -5 rather. We would not say that the absolute maximum is -5. The absolute maximum is 27, the height, the y value of the function, and where it occurs is an x value. In this example here, we have a function f of x on the interval from -2.5 until 3. Again, just as a reminder, intervals are x values. We look at an interval from left to right. Our absolute maximum, we actually have one absolute maximum, but it occurs twice. That would be the only way that it could occur more than once. It's the same maximum value occurring twice. Let's see if we can find it. Well, it occurs here and here. that maximum value is 16. It is the highest point taken on. So our absolute maximum is 16, and it occurs 2 times. It occurs when x is -2, and it occurs when x is 2. The coordinate point -2, 16, and the coordinate point 2, 16. Moving on, our absolute minimum, our absolute lowest value, is all the way down here at the right endpoint. That minimum value, it looks like it's right in between here, so it looks like the minimum value is -10. And where does it occur? It occurs when x is 3. The coordinate point 3, -10. Now, part C, I put relative maximum, ? We actually don't have any relative maximum points. You could argue that 16 is a relative maximum as well as an absolute, but I don't want to get into nitty-gritty semantics here. We actually don't have relative maximum values here. We only have an absolute maximum at 16. However, we do have 2 relative minima, and they are occurring here and here, because those are lowest points in their general area around around function values near them. They're the lowest points, but they're not the absolute lowest point. That was our absolute minimum of -10. So our relative minimum, and here I don't really care what they are, I care where they occur. They're occurring when x is -2.5 and when x is 0. The extreme value theorem, or EVT, requires knowledge of what extrema are. So now that we know what extrema are, the extreme value theorem states that a function must be continuous on a closed interval from a to b. If we have that continuity from one x value to another from a to b, then the extreme value theorem tells us that that function f must attain both an absolute maximum and an absolute minimum. Those absolute max and absolute min must occur somewhere in the interval from a to b. So this is a very mathematical way to write the extreme value theorem. Basically, in student-friendly language, the extreme value theorem says that if we are continuous, then we have extreme values. Here is the more student-friendly language. I do like to put this mathematical language in there because it is something that you will see more often in college, so we don't need to be overwhelmed by it in any sort of way. Now, I want to review what continuity means. Remember, a function's continuous if we do not ever have to lift up our marker or pen as we are drawing it. It can come to a point, that's completely fine, but we can't have any holes or gaps or jumps or vertical asymptotes. If we have those things, then our function's not continuous, and we cannot use the extreme value theorem to guarantee absolute minima and maxima in that interval. In these 2 examples, we want to see if we can use the extreme value theorem to guarantee that there are absolute extrema on each interval. Basically, in order to use the extreme value theorem, we have to have continuity on the interval from our a value to our b value. In part A, our a and b values, respectively, are -3 and 5. So, is our function continuous from -3 to 5? No. The issue is here, occurring at when x is 2, because we have a hole, we have a removable discontinuity here. Therefore, since we have a discontinuity, we are not continuous. Because we're not continuous, we cannot use the extreme value theorem. The extreme value theorem has to have continuity on an interval from a to b in order to guarantee any absolute extrema. Now, that doesn't mean that they're not absolute extrema. There definitely are, and we could find them. However, we cannot just use the EVT to guarantee that there are absolute extrema because we're not continuous. In part B, we have the absolute value function shifted down a certain number of units, and we want to see if we can use the extreme value theorem once again to guarantee absolute extrema on the interval from -1 to 20. So here's our a and b value. Now, is this function continuous from -1 all the way to 20, wherever that may be over here? Yes. Even though it comes to a point, it comes to this corner here, we are still continuous. We're not differentiable, but that doesn't matter. We are continuous. We do not have to lift up our pencil or marker or whatever at all through this function. There's no holes, gaps, jumps, or vertical asymptotes. We are continuous. So yes, the extreme value theorem will guarantee absolute extrema on that interval. What would those extrema be? We could see that the if we wanted to just sort of draw it in. If this was -1, it's not going to be very, artistically perfect here. It's clearly not 20 units, but that's okay. We could see that this would end up being our absolute minimum down here, and our absolute max would be whatever this coordinate point is up here. This function is actually continuous everywhere, therefore it's continuous on this specific interval from -1 to 20. Therefore, because we have continuity on our interval, the extreme value theorem can be used to guarantee that there are absolute extrema, a max and a min, on this interval.